Okay, hello, good morning or good evening. My name is Antonio Pan, and first of all, I'd like to thank the organizers for the opportunity to participate in this meeting. This talk is about the integrability of differential equations by means of a new notion that we have called cinf-structure. This is a joint work with Adrián Ruiz, Concepción Muriel, and Juan Luis Romero. And this is an outline of the contents of the speech. We will start by remembering some basic notions. Let's start with distributions. Distribution of vector fields is nothing but a subbundle of the tangent bundle of a manifold. Instead of a general manifold, we will consider an open set of Rn that we can shrink whenever we want. So we can consider that the distribution is given locally by R pointwise linearly independent vector fields. We will use this notation here with this calligraphic S. And an important feature usually required to distributions is involutivity. Remember that this means that the set of sections of the distribution is closed under the Lie bracket operation. Well, there is a kind of dual approach to distribution and involutivity by means of the notions of Pfaffian systems, in a sense, collection of one-forms, and differential ideas. Remember that a Pfaffian system generated by a single one-form is called a Pfaffian equation. In case you have an involutive distribution, the ideal generated by the corresponding one-form is differentially closed. In both cases, what you have for sure is the existence of integral manifolds of dimension R by virtue of the classical Frobenius theorem. The main examples of distributions important for our purposes are those arising from a system of ordinary differential equations like this. If you have a system like this, you can consider the corresponding jet space, seeking a big Rn, where we consider the variables and the derivative of the variables as coordinates. And in this space, we consider the vector field here, which encodes completely our system of ODEs. The solution of the system is given by the integral manifolds of the distribution generated by it. We can think of a visualization like this in the case of a single ordinary differential equation. Another important idea to have in mind is that of symmetry. A symmetry is an external vector field to the distribution, satisfying this condition here with respect to the vector fields of the distribution. The visual idea of symmetry in the case of an involutive distribution is as follows. If we imagine the integral manifolds of our distribution, the vector field X is just that at an infinitesimal level has the right length, in the sense that when we move through his flow, we carry integral manifolds to integral manifolds. The following important concept is that of solvable structure, introduced in the 90s. The definition refers to a kind of chain of vector fields in such a way that given a distribution set, the first vector field x1 is a symmetry of set. Then we incorporate this vector field to set and consider a bigger distribution and require that the vector field x2 is a symmetry of this new distribution, and so on. In general, xk is a symmetry of the previous distribution. Visually, we can see it in the following way. I have pictured the integral manifolds of Z like curves, but they are of dimension R. We imagine that R dimensions are compressed into one. The first vector field has to be a symmetry, carrying integral manifolds to integral manifolds. And now we add this vector field to Z, obtaining a bigger distribution. And the following vector field, x2, has to be a symmetry of this new distribution. We could continue in the same way, but I cannot draw it because I've run out of, of dimensions. The main result concerning solvable structures says that the knowledge of a solvable structure for a distribution let us integrate it. That is, to cover its integral manifolds by means of quadratures, at least locally. Remember that we are allowed to shrink down our domain whenever we want. Okay, let's change the topic for a moment and talk about symmetries of ODEs. Let's remember the classical notion of Lie-point symmetry, which is based on a prolongation formula together with an invariance criterion. But for our purposes, we'll consider, instead of this definition, this characterization. The prolongation to the Z space of a Lie-point symmetry satisfies this Lie bracket condition, as you probably know. With this in mind, it was natural to define generalized symmetries as vector fields already defined in the Z space, satisfying this same condition. Of course, Lie-point symmetries are a particular case of generalized symmetries. Observe that all of them are, therefore, symmetries of the distribution SZ, where Z is the vector field of the equation. Lie-point symmetries do not always exist, and on the other hand, generalized symmetries always exist, but are difficult to find. And so in 2001, Muriel and Romero presented a new type of vector field called infinity symmetries or lambda symmetries, with more changes to be found, and which also lead to the reduction of equations. This definition is based on a new way of prolonging vector fields to the Z space and in the same invariance criterion that Lie-point symmetries. The advantages of this concept are that let us reduce the ODE, as we have said, and that they are easier to find than generalized symmetries. But the drawback is that in the reconstruction process, you may need to solve a first-order ODE instead of simply a quadrature. In terms of the Lie bracket, C-infinity symmetries have a similar characterization, but now you have to allow a multiple of this infinity symmetry to appear in the result, contrary to the case of generalized symmetries or Lie-point symmetries. Therefore, infinity symmetries are not symmetries of the distribution SZ, but they are some other thing. So with all this background, we are naturally led to the main definitions of our present work: infinity symmetries of distribution and infinity structures. We gain the definition of symmetry of distribution by allowing that the vector field of the symmetry appears in the result of the Lie bracket. We arrive to the definition of C-infinity symmetry of distribution. Okay? Observe that this definition is a mix of symmetry of distribution on the one hand and C-infinity symmetry of ODE on the other hand. To visualize this definition, imagine the context of a symmetry X for an involuntary distribution Z, and a infinity symmetry Y can be understood as a multiple of X. This makes them easier to find. This is the key, the key feature. Now, the natural step is to define infinity structures following the idea of solvable structure. But in this case, we allow to the vector fields of the structure to be infinity symmetries. That is, we again have an ordered collection of vector fields, y1, y2, and so on, in such a way that y1 is a C-infinity symmetry of Z, and y2 is a infinity symmetry of Z together with y1. In general, yk is a infinity symmetry of Sxk. From a visual point of view, like before, we have the integral manifolds of Z comprises two curves, and the vector field y1 is a infinity symmetry. The vector field x1 is the underlying symmetry, which is not needed in the procedure, but I have drawn it for visualization. And then we consider the distribution consisting of Z together with y1. Now y2 is a vector field, which is an infinity symmetry of the new distribution. You can see that y2 has not the appropriate length. The main result obtained by us is that the knowledge of a infinity structure of a given distribution set let us obtain the integral manifolds by solving n-r completely integrable Pfaffian equations. That is, we obtain a Pfaffian system by means of the integral product of the vector fields with a volume form omega. And it turns out that the first one, or the last one, depending on how do you look at them, is Frobenius integral. We solve it and restrict all the one forms to the level sets of the solution by pulling back with a suitable map. Okay, this one form with now is Frobenius integral, but not before the restriction. And we'll repeat again. We solve it and restrict, and so on. At the end, after n-r step, we arrive to the last one, or the first one, and observe that at first only the first one form is integrable. The others only get integrable after restriction. Also, in every step, the restricted one forms have one variable less. So in general, they become easier to solve. Hopefully, we will understand this better with the examples. Okay, the pros and cons of this method. The clear advantage of this approach is that infinity structures are easier to find than solvable structure. There are more chances to find it. But the drawback is that a quadrature is no longer enough. You have to solve a first-order problem. More specifically, in the case of a solvable structure, you have closed one forms, so they are locally exact, and you can find a primitive f by means of a quadrature. But now our one forms only are completely integrable. That is this condition here. So we know that there exists mu such that mu omega is closed, and then you can find f. Anyway, in practice, we use this equivalent condition, which gives rise to a partial differential equation system, which, as listed in our samples, have turned out to be easier to solve. Okay, let's move on to the samples. The first one is a Lotka-Volterra system, three-dimensional, with these associated vector fields. This is easy samples, only for illustration purposes. We have found this infinity structure. You can check with the Lie bracket that y1 Yes, in this is in infinity symmetry, but indeed is a symmetry of Z, and Y2 is a infinity symmetry of Y2. Y3 could be any vector field, it's not important. Then we construct this list of one forms. The last one is Frobenius integrable, so we solve it and find this first integral of this one form. We restrict to arbitrary level sets with an arbitrary constant C3, and pulling back, we obtain this new omega2 with one less variable. It doesn't depends on Z. Now we solve this second Fabian equation, obtaining this other smooth function. We again restrict to the level sets with this map, obtaining by restriction, by pulling back, this new one form, which is again integrable. So we solve it, obtain this last smooth function, and at the end, again, construct this appropriate map, and the composition of these three maps give us the general solution to our system. And this is xt, yt, and zt. Our second example is a third order ODE with this associated vector field, and which has these two Lie point symmetries. If we use these two Lie point symmetries, we arrive to an equation, a reduced equation, whose solution is written in terms of the Bessel functions. So we cannot go back to recover the solution of the original ODE, because we cannot isolate in the Bessel function. But we have constructed this infinity structure, which are not the symmetries, they are constructed in the sense of infinity symmetries. Y1 is a infinity symmetry of Z, Y2 is a infinity symmetry of Z and Y1, and by applying the same procedure, we arrive to interesting solutions, interesting stuff. The first Pfaffian equation is this. It can be solved obtaining this smooth function, restrict to the level set, and obtain this new omega2 by pulling back. The second Pfaffian equation is also Frobenius integral. It was not Frobenius integral at a first moment, but it is now after restriction. And here it appears the Bessel function. It's unavoidable, and they have to appear in one moment or the other. But now they are in a good moment, because we can continue with the procedure and isolating the U1, we obtain by restriction, by pulling back, this new omega1, and solving, we obtain this expression here, and if we restrict, we obtain this general solution, which is a nice expression. It's not wonderful, but it's better than nothing. We have nothing before this procedure. If we apply the same procedure, but taking here not an arbitrary C3, but C3 equals 0, we apply the same steps, and we arrive to this closed expression, which is a two-parameter family of solution, which is good, it's nice, and it's really this is the exponential integral. Quickly, I don't want to run out of time. the expression, the equation of the paper, our work, which is it has only one lead point symmetry, and we construct this infinity symmetry, infinity structure, which led us to arrive to this beautiful general solution for it. Otherwise, you don't have anything. That's all. I want to remark that our work has been recently published 1 week ago in the Journal of Differential Equation, and you can find a link to the preprint in my archive or in ResearchGate. Thank you very much for your attention.